Hi, everyone. So welcome back. I think this video kind of is the culmination of your learning in chapter 7. And it's probably going to feel very steep when you think about the content in this video. So please make sure that you actually review or you have a good feel for, not review, like I'm pretty sure you guys are all like looking through the videos and like trying to do your work. So please make sure that you have a good feel for what does an SN2 reaction look like, how does it work, what does an E2 reaction look like, how does that work, what are SN1, E1 reactions, their mechanisms, what are some things that you need to keep in mind, things like that, okay? So because in this video here, we're basically going to use these reactions to now actually synthesize compounds or actually think about what the starting material might be to make a particular compound, okay? And for a lot of stuff that we'll be discussing here, this would be focused mainly on SN2 and E2 reactions, because realize that SN1 and E1, they always compete with each other, and so because of that you're going to get mixture of products. We don't want that here. We want to make one compound as a major product, okay? We want one reaction to be going on. We don't want several things happening in these cases, okay? So what we're going to do here is, so this video we're going to discuss chapter 7 and actually some of chapter 10 here, okay, chapter 7 and 10. And we're basically going to keep building on this throughout chapter 8 and 9. I will show you some things. It's not going to be exhaustive, okay, but I'm going to show you how we use all of these reactions and how do we build on these reactions. How do we use this for synthesis? How do organic chemists use these reactions, let's say in a pharmaceutical industry, when you have to make a drug molecule or something like a pharmaceutical drug, any of those things when you have to synthesize, how do we go about it? So within our current limitations, like we only know a few reactions, but we'll try to use those reactions and come up with some examples, okay? So what are the sort of things that we will discuss here? So and we can start simple, okay? We can start simple. So let's say if we have a product or some molecule, okay, some compound that we're looking at. Let's say that compound here, okay? And this is a product, okay? So we want this compound as a product. Now, in terms of functional groups, this is an ether molecule, okay? But I think at this point, it really doesn't tell us like a lot about how to make this. So we might have to like actually think about, okay, what are possible starting materials, okay, for making that compound as a product. In fact, actually, I want to draw this molecule here. Not there. I'm going to draw it here, okay? This is our target or our product that we want, okay? And we want to come up with possible starting materials for this, okay? So this kind of analysis is called a retrosynthetic analysis, where you actually have a final product and you're now thinking about, okay, how do we make this molecule? So because this is what organic chemists do oftentimes, because when you, let's say if you extract a compound from a plant or some natural source, and you test it for like maybe antibacterial or like any sort of activity, antiviral maybe, you know, or antifungal activity. You try it for that, you screen it for like some biological activity, and you find that, okay, it's really good. It is a good antibacterial, you know. And now you can only extract so much of this compound from a natural resource. So now organic chemists, they actually have to like look at that structure of the compound and then think about, okay, how could I make this in a lab, you know, synthesize this in bulk so that then it is more widely useful and applicable. Okay, so that's the kind of thing that we're trying to like practice here and train our minds. Okay, so for this molecule here, we have an ether. Okay, and this is a target that we want to make. So when you think about the reactions that we've done, in principle, we could use an SN2 kind of reaction to do this, to make this product. And why do I say so? Because when I look at this product, this oxygen, okay, this is del negative, and this carbon here is del positive, and so is this carbon. They're both del positive. And we've seen similar analysis when we were making products in SN2 reaction, because realize that what happens in an SN2 reaction is, okay, in an SN2 reaction, what happens is you have an alkyl halide. I'm using an alkyl bromide, and there is a reason that I will be using alkyl bromides mostly in these analyses, because remember that alkyl bromides are made from alkanes, or alkyl halides are made from alkanes through free radical reactions, and alkyl bromides can be synthesized more selectively. Okay, so that's why I'm using an alkyl bromide here as an example. So you have an alkyl bromide, right? When the alkyl bromide reacts with a nucleophile, in the alkyl bromide itself, this bromine is del negative, this alpha carbon is del positive. Okay, the nucleophile comes and attacks the alpha carbon, the bromine gets kicked out, and we make our product. So this is del positive, and then usually in most cases what we've seen is the nucleophile is something with a del negative to it. Okay, and out comes the bromide. So based on this reaction here, which is an SN2 reaction, I think we're looking at something similar to this here. So what that means is these carbons that are del positive here, they could both be, or they could have been, okay, they could have been the alpha carbon at some point. So possibilities are, I could break the bond here. Okay, so maybe that's an alpha carbon, or this could have been an alpha carbon. So I could break the bond here. Okay, so that means a product like this, it could be formed from, it could be formed through two pathways. And when we are doing retrosynthesis, we use these retrosynthetic arrows, okay, to say that this is what the starting material could have been. Okay, so we're going to use retrosynthetic arrows to say that that is possibly the starting material. So this is not going forward, this is saying, okay, this is where it could have come from. Okay, so for a product like this, it is possible that I cleave between the oxygen and this carbon. That alpha carbon is del positive in the product. So that alpha carbon, if it is del positive in the product, that should have been connected to an alkyl halide in the starting material. Okay, so that's del positive. So our starting material could be that alkyl bromide. So you basically connect a halogen to that alpha carbon, that bromide. And if that is an alkyl bromide, if this portion is what's coming from the alkyl halide, then all of this must be coming from our nucleophile. So that means this alkyl halide plus what we have here is OCH3 with a negative charge on that oxygen. So sodium methoxide essentially. This combination when they react with each other, it would give me this product, okay? The other possibility, basically dissecting it on the other side, it would mean that this alpha carbon here should be connected to a halogen. Now, this alpha carbon is just a methyl group. So we have CH3 with a Br. And if that's your alkyl halide, then all of this here, okay, to the left of that dissection that I'm showing, that must have come from our nucleophile. So all of that is our nucleophile. So our nucleophile is an ethyl group connected to an oxygen. So that means this plus oxygen with a negative charge and maybe a sodium. And I'm just throwing in some sodium ion or some potassium ion, some lithium ion, anything like that, metal, to balance that charge. So both of these would give me the same molecule as the product, okay? The O minus here could come and attack the methyl group. The bromine would get kicked out, and that would give us this product. Or the O minus from the methoxide could come and attack that alpha carbon, and the bromide would get kicked out, and it would still give us the same product. So this is our alpha carbon, this is our alpha carbon, this is del positive, this is also del positive, the bromine is del negative, the bromine is del negative here. Okay, so that's a retrosynthetic analysis that we've done based on SN2 reactions to predict what possible starting materials could result in this product. Now we can go further, okay, because these are both SN2 reactions. So we can actually talk about which of these two possibilities is better. Is there something in these combinations that tell us which one's better? So think about SN2 reactions now. We are looking at two different alkyl halides. We have two different nucleophiles. What sort of conditions favor SN2 reaction? What alkyl halide does SN2 best? It's a methyl halide, right? So when we compare this, what we're looking at is a methyl halide versus a primary alkyl halide. And what we know from SN2 reactions is methyl halides, they're really good at SN2 compared to a primary alkyl halide. They're the best. So maybe this pathway here is the best way to do it, not the top pathway. But what I can tell you is that in this particular case, because we are comparing a methyl halide to a primary alkyl halide, it really doesn't matter. I think both of them would give like a very good reaction to give this product. But that sort of analysis would be useful when we look at like other examples. So let me go to another example where this analysis would be really important. Okay, so let's go into that. So the next molecule that we look at is so let's say we have this. That's a target molecule or the product that we want to make. Okay, so again, since we have this oxygen here, that carbon is del positive because the oxygen itself is del negative in the molecule, and this carbon here is also del positive. And now we can dissect the molecule two ways. Okay, so we could break the bond between the oxygen and this carbon, or we could break the bond between oxygen and the other carbon atom on the right hand side, either one of those. And the carbons that are del positive, those are the alpha carbons from our alkyl halides. Okay, and what I want you to realize is at this point, we only learned the reactions of alkyl halides, so this analysis is very easy, okay? But as we go through this process, we'll have to learn how to identify this for like a lot of reactions, okay? So our analysis here, okay, what are our possibilities, the retrosynthetic analysis? So let's say if it is breaking the carbon-oxygen bond on the left-hand side, the carbon that's del positive, that should have the halogen. And then everything on the right-hand side here, that is our nucleophile. That was a nucleophile. So this plus sodium ethoxide, essentially, okay? Oxygen with 2 carbon atoms. If we break it on the right-hand side of oxygen, so if it is the other dissection or the dissociation that we're looking at, then our carbon, which is the del positive, that's the carbon with the halogen, okay? So that means we have 2 carbon atoms with a halogen attached to it, okay? It's a 2 carbon alkane with a halogen now on that carbon with the del positive. Now, I just switched it over. So these things should not be confusing at this point, okay? So this is del positive, this is del positive, this is del negative, this is del negative. And then our nucleophile would have to be everything to the left of that dissection, essentially, okay? So oxygen and everything to the right. So that is, I don't think I need that. This plus that. So those are 2 options which would both give us this product that we want. And so now if we analyze this, we have a secondary alkyl halide and a primary alkyl halide. Okay. And what we know from SN2 reactions is that primary alkyl halides do a SN2 reaction much better, faster, they're more reactive compared to secondary alkyl halides. So that means the preferred pathway for doing this to make this product would be this bottom dissociation. It would be better than the top one because we have a secondary alkyl halide with a strong nucleophile, strong base. So that means a secondary alkyl halide could now give you elimination, E2 reactions at the same time. Whereas a primary alkyl halide would give you SN2 reaction. So now you can favor your product and not have a competing reaction going on, okay? So that's 2 examples of SN2 reactions. Now, we can do the same sort of retrosynthetic analysis for alkenes as well. And we will see how to combine these things, okay? So let's say if you want to make an alkene, and we want this alkene as a major product. Yeah, let's say that's the alkene that we have. Okay, let's say that's the alkene. We want to make this alkene from something. What would be a suitable starting material to make this alkene? We have to do a retrosynthetic analysis. Okay. So in this particular case, when you have alkenes, okay, we learned E2 reactions that help us make alkene products. So what you have to think about is, where is the double bond formed in an E2 reaction when you make an alkene? And based on previous videos, realize that the double bond is always formed between the alpha and the beta carbon. So since we have a double bond here, this could be alpha and the other carbon could be beta, because the double bond always forms between the alpha and the beta carbons. And if that's true, then what we're looking at here is the retrosynthetic analysis for this. If that's the alpha carbon, that's where the halogen was. So, and then the beta carbon should have had the beta hydrogen in the alkyl halide. So that means a suitable starting material for making this alkene product would be this, okay? This is our alpha carbon this is a beta carbon. Now realize that this is only one of the beta carbons. This alkyl halide has a beta prime here, and it has a beta double prime over there. So there are 3 unique beta carbons in this alkyl halide. But if we react this alkyl halide with a strong base, so let's say if we react with sodium methoxide, this alkene here is going to be our major product. Okay, this alkene would be the major product. The reason? Because this is the more substituted alkene. So that's another analysis that you have to keep in mind. So we have an alkene. So what we have here is an alkene, and it's actually the more substituted alkene that's possible. So this is one retrosynthetic analysis. I think there's another way that we can do this, because it does not have to be alpha over there. Maybe alpha is the bottom carbon and beta is the top carbon. And if that's the case, then our starting material is going to be this molecule here, plus a strong base. That would still give us this product, because the same alkene product, because this is alpha, and now we have beta, beta prime, and then we have beta double prime. And beta double prime, that hydrogen at the beta double prime position, that's going to give us the most substituted alkene. The more substituted alkene, which is going to be our major product. So we can basically do this for elimination reactions also, okay? So we can predict what's our starting material. I want to show you another example on E2. And again, SN1, E1, we will not be considering here because they give us mixture of products. They always compete with each other, okay? So let's say we want this alkene now. Okay, that's the alkene that we want. So for this alkene now, again, the double bond is formed between the alpha and the beta carbon. So let's say this is alpha and this is beta. That's one of the analysis that we've done, okay? That this is alpha, that's beta. So if that's true, then our alkyl halide and the reagent are going to be this. Since that's the alpha carbon, that's where the halogen would be connected to, okay? And then the beta carbon should have the hydrogen, the H beta. So that's the alkyl halide. So we're going to react this alkyl halide with a strong base. So let's say sodium methoxide. Okay. The other possibility is this carbon is alpha and this carbon is beta. Now, our starting material here is an alkene, but in this particular case, let's say if this is the alpha carbon, or either ways, realize that there are more substituted alkenes that are possible here. Okay, this is an alkene, so we'll get into that later. So if the bottom one is true, if alpha and beta are those, okay, so for that case, when alpha is this carbon, the tertiary carbon is alpha, and beta is the primary carbon. We looked at the other option where beta was the tertiary carbon and alpha was the primary carbon. So if it is the other way around, then the alkyl halide that we're looking at is halogen at the alpha carbon and plus sodium methoxide. Those are our possibilities, okay? But now let's think about these. are these correct? Okay, because we have to also analyze these now that we've come up with these options. Okay, so if we look at the first case here, the alkyl halide that we have, this is a primary alkyl halide. We have sodium methoxide, which is a strong nucleophile and a strong base. Okay, it is a strong nucleophile as well as a strong base, which means it can both deprotonate and it can actually act as a nucleophile. And since our alkyl halide is primary, chances are that this is mostly going to do an SN2 reaction here. Okay, it's going to do an SN2 reaction, which will not give us this elimination product. So how do we get this situation here, or how do we get an elimination in this situation here? We have to change our base to a bulky base. Okay, so we're going to change this out, switch this out with a bulky base. So let's say potassium third butoxide, potassium T butoxide. If we use the bulky base, now the bulky base cannot do a substitution, so it could actually do an elimination instead. Okay, so this O minus here, this will not do this. Instead, what it's going to do is it will go for that H beta. Okay, because there is no other option here. Okay, in fact, in this particular case, I think you're going to get a competition. Okay, because that is bulky and this H beta is tertiary. So I think you're going to get a competition between your elimination and your elimination and substitution reaction. So this is SN2 and this is E2. And there will be, both of them are not favored in this particular case because it's a primary alkyl halide with a bulky base, so substitution is not favored. Bulky base with a tertiary beta hydrogen, even that's not favored. So this may not be the best way to do it. Let's go to the next one here. So we're analyzing this before we come up with which is the best option. So let's say go to the next one here. Now we have a tertiary alkyl halide. We have a strong nucleophile, strong base, but the alkyl halide is tertiary. That means we cannot get any SN2. Okay, but since this is a tertiary alkyl halide and there are two unique beta positions, so we have beta hydrogen, H beta, and we have beta prime hydrogens. There are two possibilities for alkenes to make. And with a small base like this, it will actually favor the beta hydrogen because that will give us the more substituted product. So from this reaction, what's going to happen is we're going to get an alkene which is more substituted. This is a tri-substituted alkene. That would be our product. That's the Zaitsev product. But what we want is this less substituted alkene. So how do we do that? We will not use sodium methoxide. Instead, we are going to use potassium T-butoxide. Use a bulky base because we want a Hoffman product. So when we use potassium T-butoxide now, sorry, I'm putting T at the wrong place. Or at least it looks like it's at the wrong place. It's next to the B, okay? So T-butoxide. Now, because this is a bulky base and H beta is a secondary hydrogen, whereas H beta prime is a primary hydrogen, the bulky base, the big base, would go and deprotonate H beta prime, the less sterically hindered hydrogen. And that would actually give us the product that we want because those electrons would come down and then the bromine would get kicked out to give us the alkene that we want. So you have to do a lot of analysis based on these reactions to predict what starting materials will be useful. Okay, so for this particular case, let's say that the best combination of reagents that would give us this product, okay, the ideal combination actually is this alkyl halide, the tertiary alkyl halide, plus a bulky base. They together would give us this product as a major product. Okay, so that's one thing. Now we'll take it up a little bit more, one level higher. Okay, where you might have to like actually think about synthesis itself, okay, where you're given a starting material and you're given a product. Okay, so let's say we have a case where you're given this starting material, and so this is your starting material. And you have a product there. And what you have to do is you have to devise a strategy to convert your starting material into the product. Okay, you have to go from here to there. Now, sometimes this is possible in one step. Sometimes it could take several steps. Okay, so we'll see how many steps this would be and what sort of analysis goes into this. So this again depends on like retrosynthetic analysis. That is what you have to do. So we will come back and fill this later, but let's do a retrosynthesis on our product. So we want this product. And I think we just looked at it a little bit ago, like another example. So to make an alkene like this, a very similar example is what we looked at. To make an alkene like this, remember for the double bond, you have alpha and beta. That's where the alkene double bond forms in an E2 reaction. So whenever you see an alkene, E2 should come into your head. So you should think about E2 reaction. So we have alpha and beta. This alkene here can be made from this alkyl halide along with a strong base. Okay, because in this particular case you have beta and beta prime, but when you do it with a regular base, your product should be the more substituted alkene. So this is the product that we're going to get. So this alkene can be made from that alkyl halide. But notice how our starting material is not an alkyl halide, it's an alkane. So you have to think further. How do you make this alkyl halide now? So that alkyl halide, retrosynthetically, how you make alkyl halides is through the free radical halogenation. So the alkyl halide itself can be made from an alkane and bromine using the free radical halogenation reaction, because this is a tertiary position. So if I take that alkane and then do a bromination on it, my major product is going to be that alkyl halide. So now I've done a retrosynthetic analysis that actually took me to the starting material I have here. Okay, so now that we have this, we can go ahead and complete this by writing the reaction in the forward order, okay, or the two reactions in the forward order. So starting from that alkane, if we did Br2 H nu with heat, okay, free radical bromination, this would give us the tertiary alkyl bromide. That will be our major product. Now we are only writing major products in the scheme. Okay, so this is our major product. We are ignoring minor products at this point. That will be our major product. And if I take this tertiary alkyl halide and if I react this with sodium methoxide, and honestly in this particular case, the solvent really doesn't matter because it's a tertiary alkyl halide, it won't do SN2. So the only possible reaction is an E2. It will give me that product, okay? It will give me that, but we can go ahead and include the solvent. So let's say this is methanol and we are heating this. So under these conditions, basically using two reactions that we've learned, free radical halogenation and E2, we can convert our alkane into an alkene product. And this is how the chemical industry operates. This is the kind of things that organic chemists do when they start from simple molecules that you get from petroleum and other natural resources and then convert it into like other molecules that are useful. Okay, so that's a retrosynthetic analysis. All of this, we need to be able to understand all of these reactions. So I will post some worksheets on these and give you like some answer keys to those reactions. Okay, but again, this is not mere memorizing. You cannot basically look at a reaction and memorize it and basically come up with this analysis. You have to understand the reaction really well, because you have to know you have to basically know all the factors that you have to keep in mind before you come up with an analysis like that. Okay, so I'll post some more examples of that and share some worksheets. Okay, bye.